I want to turn your attention now to the case that we'll encounter when we see non-ideal solutions. The truth of the matter is, most solutions are not ideal. Even though the ideal solution gives us a convenient benchmark to look at these, we need to understand how different solutions might deviate from ideal behavior. So I want to remind you that an ideal solution is one where all interactions are the same. That is, all of the forces between molecules are the same, whether they're uh, the same molecule or different molecules in a mixture. Now we're going to deal primarily with a binary mixture, and I want to label these. I'm going to have two components in my binary mixture, A and B, and I'll arbitrarily label A as 1. So if I slip up and use 1 as a subscript, I'm referring to component A, and 2 for B. All right, so when I say that all interactions are the same, what does this really mean? Well, what it means is that the interactions between an A molecule and a B molecule are essentially the same as the interactions between two A molecules, and those are the same as those between two B molecules. So in other words, the forces that these molecules are feeling with one another are going to be pretty much the same. And so in an ideal mixture, we find that all properties tend to be dependent upon their mole fractions or the proportions of these two components in the solution. So, as an example of that, we had Raoult's law that said that the vapor pressure of a component, so I'll just use a generic J for that, the vapor pressure of component J would be its mole fraction in the solution times the vapor pressure of its pure component. We also would have such things as the chemical potential for component J in the solution would be equal to its pure chemical potential plus RT, and then because of this relationship with Raoult's law, it's dependent upon the mole fraction of that component. All right, so what happens in a non-ideal solution? What can we expect to see? Well, first of all, since it's non-ideal, all of the interactions will not be the same. So I want to alert you to two possibilities. And, these are generally the possibilities you're going to see in practice. Okay, the first possibility is that our interaction between different molecules is not as strong as the interaction between similar molecules. So it's not as strong as the AA interactions or the BB interactions. So we could say that this represents a weaker interaction. So they're not going to stick together as well. And that implies also that it's easier to vaporize. So in other words, when they're not being held as strongly in the solution, as they would be to each other, when I don't have a full set of molecules that are just one thing, then it'll be easier for them to escape. So what we might see in that case, if we were to draw it on a diagram, and I've drawn here basically a vapor pressure diagram for a pair of gases, and I've indicated what the Raoult's law behavior would be, for example, if I were to track the vapor pressure of pure A or the vapor pressure of pure B. This is sort of what it would look like, and of course the Raoult's law sum of these two would give you the total vapor pressure for the mixture. All right, when the two molecules don't react with each other or don't interact with each other as strongly, what would that look like? Well, when these mole fractions are not at the two extremes, what will happen in that case is that these things are easier to vaporize, so they're going to show a greater vapor pressure than the one they would have shown in a Raoult's law case. So for example, for component B, I might have a curve that would look something like this, and it will actually, as it gets closer to pure, sorry, I've labeled that A. I should have labeled that B. Sorry about that. This should be B. Okay, when B gets closer to pure, it's going to look more and more like our Raoult's law vapor in that instance. Okay, the same token for partial pressure of A, which I'll put over here, it will start off up and then it will again approach the limit of the Raoult's law as it gets closer and closer to being pure A. Now, how might we justify that? Why is it getting closer? Well, think about what happens when I have a solution, for example, where xb is near 0. Okay, what is most of that solution made up of? Well, if the mole fraction of B is mostly 0, then it's mostly A molecules. So the partial pressure of B is going to mostly reflect the interactions of A with B. So that's why it's going to be larger in this segment than the Rolle's law segment. It's easier to vaporize. All right, as it gets closer to its pure limit, that's where xb goes to 1. And in that case, most of the molecules, in fact all of the molecules in the mixture, are B molecules. So that means we're looking mostly at B-B interactions in that case, and that's why it tends to look more and more like the pure B component. The same would be true for component A, shown in this second curve here. So it would mostly see B molecules when it's at this end of this graph, and mostly see A molecules when it's at this end of the graph. Now what this means is when I add these two together to get the total vapor pressure, I'm going to get a deviation from this linear fit to something that goes up above the vapor pressures for these two things. So we see what amounts to a positive deviation. So you should be correlating a positive deviation from Rolle's law behavior with interactions that are weaker between the two molecules, and so therefore maybe more repulsive. It makes it easier to vaporize these things. Now you should also note that when it's easier to vaporize, that means that the vapor temperature, the vaporization temperature, is going to be greater. Easier to vaporize means it's going to be smaller. I'll get this right one of these days. Okay, so this is the case for that first possibility. The second possibility, I think it's probably easy to anticipate, is going to be when the interactions between A and B molecules are greater than the corresponding interactions between A molecules and B molecules. Okay, so they're being held together stronger, so it's a stronger interaction, which means it is harder to vaporize. Okay, and likewise we can assume that the temperature of vaporization will be larger. All right, as I tried to indicate in the previous one. All right, so again, as we draw this on this other plot, and let me draw the Rolle's law total pressure again on this plot, straight line. Okay, now it's harder to get these things out of the solution. So that means that when I'm starting here at 0 of B, it's going to deviate from the line, and as I get closer and closer to pure B, it will again merge and look more and more like the Rolle's law formula. Same will be true for component A, and it will be a curve that looks something like this. Okay, the shape of these curves is completely typical. We'll talk about them a little bit more when we discuss Henry's law. But that means now that the deviation from the Rolle's law total pressure is going to be a negative deviation. So I'll write that up here, negative deviation. So a negative deviation suggests that these interactive forces are going to be stronger between the different molecules than they are between the molecules with themselves. All right, once again we can draw the same kinds of conclusions. As the mole fraction of B goes to 0, we're at this end of the curve, it's going to see mostly A molecules. So I'll say C's mostly A. So the interactions that count the most are going to be the AB interactions, and they're stronger. So we'll see that negative deviation as shown down here in the plot. We'll see that negative deviation for the vapor pressure of B. I should have labeled this as pressure of B, and this is pressure of A. Okay, so likewise, when we get close to 1 for that mole fraction, then these B molecules will see mostly B. And that means that it will look more and more like a pure substance. So this is what the interaction will be like. So we'll find that the vapor pressure of B will approach the pure vapor pressure of B, very much like it does in Raoult's law. And similarly, we'll see very similar kinds of interactions for component 1, or component A in this case. All right, now the one thing that I want to highlight here, another thing I want to highlight, is what we can draw, inferences we can draw from certain graphs. So what I want to draw for you here is a similar sort of graph, but I'm going to draw it for 3 different molecules, that is to say in 3 different mixtures. So what I want to look at are alcohol-water mixtures. And I'm going to normalize these so that the vapor pressure of the alcohol is the same in all cases. So I'm just going to come up here to a generic vapor pressure of the alcohol, and this is the pure vapor pressure is up here. And this represents the mole fraction of the alcohol down here. The remaining material in this is all going to be water. And what will these look like as I go, for example, from methanol, and I'll leave this in blue, I'll go to ethanol in purple, and to propanol in red. What will these deviations look like? Well, first of all, in this case, it turns out that there is a positive deviation from Raoult's law in all of these cases. In the case of in the case of methanol, it's a pretty small deviation because methanol and water are about the same size and they both do hydrogen bonding, so we'll see a curve that looks something like this. When we move to ethanol, now we've got a little bit more of a hydrocarbon there, and it turns out that the deviation from Raoult's law is a little bit bigger, and we'll see a curve that looks something like that. Finally, as you can anticipate at this point, I hope, for propanol we'll see the biggest deviation yet, and then it will come down and join a Raoult's law behavior. So what we're seeing basically is that the larger the hydrocarbon, the greater the effect. So let me write that down. Larger hydrocarbon leads to a greater non-deviation, a greater non-ideal effect. And that's because the hydrocarbon part is actually it's hydrophobic, so it is going to avoid waters in that case. It becomes harder for these molecules to stick to one another. It's easier to liberate them into the gas phase, so we see that deviation come through when we graph these sorts of things for these alcohols.